Hi everybody and welcome. Today we're going to be looking at geometric proofs. So if you remember on the first day that we did real math content in geometry this year, we talked about algebra proofs, where we were doing things like proving properties with, addition and subtraction and multiplication and division. So those are all things that we have from algebra. Now what we're going to start for the first time is looking at proofs from geometry, and these geometry proofs use properties that we've learned in class so far this year, use the definitions we've learned in class so far this year. So no longer using addition and subtraction. Instead, we're going to be taking a look at some different specific things that we see in the geometry class. So definition for today is geometric proof. And this is an argument that begins with known facts and uses logical deductions to reach an answer. So a couple things to remember is that every time that you have a proof, you have a given statement and a prove statement. The way that we structure proofs is on the left side we have our statement, and on the right side we have our reason. And the first thing that we always have in our first line, no matter what, is what is given to us. So just a reminder of some of the basics of our algebra proofs, and it really just depends on the question. If we're taking a look through each of these one step at a time, we're really going to have to go and find each property that we use to get from the first line to the second line and so on. So we're going to talk about each of the properties that we have here, and we're going to be able to move on from there. So the first one is reflexive property, and this is one of my favorite ones. Reflex just means something is itself. So there's nothing new being gained here. All that we're doing is saying that if you have 1, 1 equals 1. 2 equals 2. 7 equals 7. Anything is exactly itself. Winnie equals Winnie. That's a reflex. No matter what, anything equals itself exactly. So in any geometric figure, if you have a side AB, what we can say is that AB is the same as itself. AB is equal to AB. This seems kind of silly to say because it's obvious, but these statements are going to help us prove things later on in the course. So it's really important that we have a good understanding of basically something being itself being a reflex. Second, we have definition of congruence, our second property here. I'll do this one in green. So for our definition of congruence, what this says is that for any geometric figure, if two things are congruent, so our congruent symbol, they are also equal. So all that we're doing is we're rewriting a line AB is congruent to line CD. What we can say is that AB is equal to CD. So you're like, okay, is this the same thing over again? Actually, no. On this side, this is a measure. So just AB with no symbol on top is a measure. It indicates a length. So in this case, if we knew that AB is 4, what we could say is that AB is equal to CD, or 4 is equal to CD. So if they give us a length for something, what that allows us to do is say that, okay, if we know that AB is equal to CD, then we know whatever A equals in terms of a number is also what CD is equal to in terms of a number. The same thing goes for angles. So if you have an angle that's congruent to another angle, we can say that not only are they congruent, they are also the same exact number measure. So the degrees of that angle is equal to the degrees of the other angle as well. Symmetry, this is one that is pretty useful for us. What the symmetric property tells us is that if we know that AB is congruent to CD, we can say it in the reverse order. So we can also say that CD is equal to AB. So again, nothing is really changing about any of these things. We're just changing the order. And this tells us if we ever see an order change in a proof, we can justify it by saying it's the symmetric property of congruence. So just something to note, we do want to make sure we're taking good notes on the exact wording here. So when we say symmetric property, we want to actually say symmetric property of congruence. So when we're answering a question on the state test, we we don't just want to say symmetry or symmetric, we do have to say the whole property out. So symmetric property of congruence. So all of those things have to go together. And the same thing goes for reflexive property, definition of congruence, everything. We got to go word for word here. Next one, transitive property of congruence. So transitive property, and I'll color code this to make it more obvious. Basically what this is saying is that if something like AB is equal to two different things, so if AB is equal to two different measures, so CD and EF, what this tells us is that in this case, if green equals red and green also equals blue, because green is the same, then we can go ahead and put blue and red together. So because AB is equal to both of these, we also know that they're equal to each other. So I think colors are the only way that I can really see this. It's kind of hard to put into words, but basically the idea here is that if one thing equals the same two things, the two things that it equals also have to equal each other. The classic example that they use for this is if A equals B and B equals C, then A equals C. You can also view this as it's kind of like cutting out the middleman. In this situation here, B is in between A and C, and all that we're doing is saying if we get rid of B, we know that A also is equal to C. All right, the last few of these are properties that we actually have been working on in class the last couple of weeks. We've used these definitions. So segment or angle addition. So line segments, that's if we have two lines and we add it together, or angle addition, that's if we have two angles and we add them together. Basically what this is saying is that we can break these into parts and we can add them up. So if C is between A and B, so if C is in between A and B, this is telling us that AC, so part 1, plus CB, part 2, is equal to all of AB, part 3. So we've actually done this in class quite a few times. All it's saying is you take the two little pieces and you add them up to the one big piece. The same thing goes for angles. So if you have one big angle, you can break it up into two pieces, and the same idea. Next, segment and angle bisectors. This is more specific, so it's telling us when we break something up into parts. So if you have a line, segment, point array that cuts a segment or angle into parts, more specifically, a bisector is telling us that those parts are congruent parts. So if we have our line AB and C is in the middle, if we are told that C is a segment bisector, what that tells us is that AC and CB are the same. So if this was a number like 2, then that would mean that this would also have to be 2 as well. So it cuts it into exactly equal pieces. The exact same thing is true for midpoint. So again, midpoint of a segment cuts a segment into 2 equal parts. So if you see a point cutting a segment into 2 equal parts, then you have a midpoint. If you see like a line cutting a segment into 2 equal parts, then you'll have a segment bisector. All right, so taking a look through at a couple of examples here, we'll do some practice with the properties that we just learned. What we are going to first take a look at is our first example. So if the measure of angle 1 is equal to angle 2, and the measure of angle 2 is equal to angle 3, they're asking us to prove that angle 1 is in fact equal to angle 3. So starting off, our first line, as always, it exactly matches our given statement. So our reason for this is that it is in fact given. Now our second line, they tell us that the measure of angle 1 is equal to the measure of angle 3. So if we go back to where we started, and we see that angle 1, angle 2, and angle 3. So if 1 is equal to 2, and 2 is equal to 3, so 2 is equal to both 1 and 2 is equal to 3, so it's equal to both 1 and 3. That brings us actually back up to our transitive property up here. So transitive property is going to tell us that if 2 is equal to both the same things, then the things that 2 is equal to must also be equal to each other. So if we cut out our middleman here, if we cut out 2, what it's going to tell us is that 1 is equal to 3. So transitive property of congruence. So in this case, what we are seeing here is that we have just got it down to transitive property 1 is equal to 3. And then on the line below, instead of measure of angle 1 is equal to measure of angle 3, it's now saying that angle 1 is completely congruent to angle 3. Well, if we remember, definition of congruence, it takes us from a congruent statement to just a measure statement. So by the definition of congruence, what we can say is that angle 1 is completely congruent to angle 3. All right, we are going to finish up with one final proof here. So in line 1, for this proof, so measure of angle A is 90, and A is equal to Z. Prove that Z is a right angle. So I'm going to have you answer what is the reason for statement 1. Well, as always, first line, given. Next, I'm going to have you answer what is the reason that we can say A is equal to Z. So this one is the definition of congruence. And the reason why we know this is because we've just changed from a congruent sign up here to just an equal sign down here. And we have the same thing on either side. So we went from just angles to the measure of those angles. Next, it's showing us that the measure of angle Z is equal to 90. So what we've done is, from this line to this line, both of the Z's are the same, so we haven't changed that. But what's happened is we've changed out the measure of angle A, and in its place, we've put 90 degrees. So we've taken something and put something else in its place. And because of that, what we can basically do here is we have a couple of options, but we can say that this is the substitution property. Alternatively, what you can also say is that we can use the transitive property here. So because the measure of angle A is equal to the measure of angle Z, and we can also say that the measure of angle A is equal to 90 degrees. The measure of angle A is equal to two things, so therefore these two things must also equal each other. So we could also say the transitive property. So either of those answers would be true in this case, so both are okay, both are acceptable. And our final step, Z is a right angle. Well, this is just the definition of a right angle. So we know that right angles are 90 degrees. In this case, we've identified that Z is 90 degrees. So by that definition that we've used before, we can say, okay, we've got it. It is a right angle. So that's how proofs work for us today. Hopefully this video helps. As always, if you got questions, shout them out. We are here to answer them for you. But again, just a lot of definitions, and we're just putting all the definitions that we already know together in